Good morning to all of you. In previous session, we have seen the realization of discrete time systems, where the discrete time systems or digital systems are described by using the difference equation, which is the combination of the sum of past outputs scaled by the feedback coefficients AK, and sum of future, present, and past inputs, which are scaled by the delay dependent feed forward coefficients BK. Right. So today we'll be discussing the basic building blocks required for the basic realization of given discrete time system. Then we'll discuss how to obtain the signal flow graph for the realized block diagram or realized discrete time system. Then we'll see the difference between canonic and non-canonic structure, and then we'll see the advantages of representing any discrete time system using block diagram. Okay, so first we'll see basic building blocks. Basic building blocks for the realization of discrete time systems. Right. So as discussed in the previous session, the generalized form of difference equation, that is y of n is equals to summation k is equals to 1 to n minus 1 ak y of n minus k plus summation k is equals to 0 to n minus 1 bk x of n minus k. This can be represented in system function form as y of z upon x of z as summation k is equals to 0 to n minus 1 bk z to the power minus k whole upon 1 minus summation k is equals to 1 to n minus 1 ak z to the power minus k. Right. So if you observe both these equations, right, so you can use any one of these two equations for the realization of given discrete time system. You can use the difference equation as it is, or you can convert the difference equation in the system function form, and then you can use that system function for the realization of this discrete time system or the digital system. Right. So if you observe these equations, so these equations simply involve the addition operations, right, or the delay operation, or the multiplication by constant operation. Right. If you observe this system function, it also involves the addition operation or the delay or the multiplication by some constant coefficients. Right. So we for the realization, therefore for the realization of the given discrete time system, we require only three basic building blocks. Okay, so first one is the adder. Okay, so or which is also called as signal adder. This will be used for the addition of two sequences. Okay, so for addition operation we'll be using the signal adder. Right. So this is the basic building block, first basic building block that we can use for the realization of digital system. So this basic building block is used for the addition of two signal, that is x1 of n and x2 of n. Second is for multiplication. Okay, so that is nothing but constant multiplier. Right. So it will simply multiply the given signal x of n with a constant small a, just for example. Its output will be a into x of n. And third one is the unit delay or delay element. Okay, so where if we apply x of n as an input signal to the delay element, then it will produce x of n minus 1 as its output. Okay, so by using only these three basic building blocks, we can realize any given discrete time system or digital system. Let's see one example here. So here you can see that one difference equation has been given. Y of n is equals to a1 y of n minus 1 plus x of n plus b1 x of n minus 1. So output y of n depends on past output y of n minus 1, present input x of n, and past input x of n minus 1. Right. So it is a first order difference equation, right, used to describe the given digital system or discrete time system, right, and we have to determine the block diagram as well as signal flow graph for the given system, right. So let's try to obtain its realization first, right. So the given difference equation is y of n is equals to a1 y of n minus 1 plus x of n plus v1 x of n minus 1. Okay, so as I said, you can use the difference equation as it is for the realization of given system, or you can convert it into system function by taking its z transform and then by representing y of z upon x of z, right. So if you see here this equation, so we'll try to directly obtain the realization for this equation. Okay, so here initially we'll be applying input x of n to the system, right. So what it is doing basically, right, so this x of n is getting added, so addition operation is performed, output will be simply y of n. This x of n is simply added here, right, with what you can say that the delayed version of x of n minus 1. Okay, so this for taking the delayed version of this x of n will be using an delay element. Okay, so here the input signal will be your x of n, right. So x of n will come here, so it will get delayed by 1 unit in time. Okay, so unit delay will be applied here, so output will be x of n minus 1, then we'll be multiplying that x of n minus 1 output with constant b1. Okay, and then this b1 multiplied by x of n minus 1 will get added with x of n here, right. So currently the output of this adder is x of n plus b1 x of n minus 1. Okay, so x of n, so it is x of n fed here. Okay, output will be x of n minus 1 multiplied with b1, so b1 x of n minus 1 will be given input here to this adder, and another input is x of n, right, correct. So here this addition will be performed, that is x of n plus b1 x of n minus 1. So this is nothing but the feed forward. Okay, so therefore this b1 is called as what? Feed forward coefficient, right, feed forward delay coefficient, right. So as in previous session we have seen that this bk is feed forward delay coefficient, while this ak is the feedback delay coefficient, right. So if you want to add this a1 y of n minus 1 into this term, so it should be feedback into this system. Okay, so therefore this feedback loop will be there. Okay, so if I'm taking the feedback of this y of n will be fed back into this delay element, right? And then it will compute the delay of this y of n, okay, if I'm using the feedback loop, right? So here the output, see the direction of this arrow in the feedback direction, right? So it is in reverse direction basically in this case. So here I can use constant a1. So output that I'm getting here in this feedback version is y of n minus 1. So this y of n minus 1 will get multiplied with a1, and then I'll be adding it by using one more adder here, right? So here we are feeding this a1 y of n minus 1, okay? So it is feedback while this is feed forward, right? So this is nothing but the required, so this figure indicates the required basic realization block diagram, okay, for the given digital system represented by the given difference equation, okay? So it is realization block diagram of given digital system, right? Now let's try to obtain its signal flow graph in this case, okay? So while solving this problem you should only draw this diagram, right? But for your understanding purpose I'll specify here the inputs which are coming here, okay? So here x of n is coming as input to this adder. Here is b1 x of n minus 1 is the another input to this adder, right? So these two signals will be added here, while to this particular adder the input is a1 y of n minus 1, right? Because it is a feedback, okay? So it is, this output will be feedback here, while this is nothing but the feed forward, okay? So forward direction arrows are there, so here it is backward direction arrows, right? Okay, so now let's try to obtain its signal flow graph, okay? So how to obtain the signal flow graph for the obtain the realization structure, okay? So here we'll try to simply represent it by using these connected nodes, right? So here you can see one adder is there, so for this adder this node is indicated here, and again here you can see that this connection node is there, right? So again you can use one more connector node here, right? Then again you can see in the previous slide one more adder is there, right? So for that adder again this node has been indicated, and then finally your output. So here the input can be specified as in time domain x of n, or in the domain it is x of z, while the output is y of n, or can be capital Y of z, denoted as capital Y of z, right? So here you can see the delay element is there, right? So for that delay element here you can indicate this as z inverse, okay? So there is nothing here, that means simply 1 in multiplication is there, right? In this case this 1 in multiplication will be there, right? While if you observe from this particular node these constants are there, right? v1 and a1. So this can be indicated as v1 while this will be indicated as A1. Okay, so this is nothing but the delay branch, right? This can also called as what? Source node, while this is called as what? Sync node, or you can call it as input node and output node, right? So this is nothing but what? The signal flow graph is there, right? And here we are using these uh, connectors here. Okay, so first one, this is for adder, this is simply for connection, this is third for again adder, and this is again a connector node, right, in this case. So this figure indicates the corresponding signal flow graph. Okay, so such signal flow graph you can obtain from the realized digital system or the realized digital system structure. Okay, so from this realization structure we obtain this signal flow graph. Okay, so this is how you can solve this example where we identified the relation block diagram as well as the corresponding signal flow graph, right? Okay, so let's see what do you mean by canonic and non-canonic structure. Okay, so canonic and non-canonic structures. So if the number of delay in the realization block diagram, okay, is equal to the order of the difference equation or the order of the transfer function of the digital system, then the realization structure is called as canonic, otherwise it will be called as non-canonic. Okay, so if the number of delay elements or blocks is equal to the order of difference equation, okay, or system function or transfer function, right, then that structure will be called as what? Canonic, otherwise it will be non-canonic. Just for example, we have just realized this difference equation. So this was the first order difference equation, and in its realization structure we have used only single delay element. As you can see that we can also use two delay elements separately here, but here we have used only single delay element, right? So when you are using single delay element, then and the in this case the order of the system is also, it is a first order difference equation, right? So order of the system or the transfer function is 1 here, as well as delay element that we used is 1 here. So therefore it will be called as what? Canonic structure, right? So if you observe this realization structure here, we have used two adders, one delay element and two constant multipliers, right? So total 5 basic building blocks were used here for the realization of the given system, right? And the structure that we obtained is the canonic. The reason for this, because we used only one delay element here, as well as the order of this system is 1, right? Our difference equation is 1. So just for example, if we are using the same difference equation, it is y of n is equals to, what is that, a1 y of n minus 1 plus x of n plus b1 x of n minus 1. Okay, so same difference equation is there, but we can obtain some different realization structure. How? So here input x of n you can take, right? Here initially you can add this part, that is x of n can be added directly in the, what you can say, the delayed version of it. Okay, so here I will be computing or connecting z inverse. Okay, so what delay element I have used, so its output will be x of n minus 1, so I am just using feed forward here, right? So this x of n minus 1 is getting multiplied with b1 and then it will be added here, right? Correct. So this can be taken as y of n. So here this y of n should be feedback into the system. So again I will use one delay element here, right? Z inverse. So this y of n minus 1 which is feedback here. Okay, this y of n is feedback here, so I'll multiply it with the constant a1 and I will use one adder here to add it into the overall, what you can say, this output, right? So see, this is another realization structure for the same difference equation, right? So again, for your understanding, I will indicate the output at every point. So here this x of n is going into this delay, so here output is x of n minus 1. Here it is multiplied with b1, so input applied here will be b1 x of n minus 1. Here another input applied is x of n. Again here the output of this delay element is y of n minus 1, okay, which is feedback into this system. So here it is getting multiplied with a1 and here input will be a1 y of n minus 1, right? While the other input to this adder is this addition result, that is x of n plus b1 x of n minus 1, right? Okay, so this is the input here, that is x of n b1 x of n minus 1, while another input is a1 y of n minus 1, right? And final output here will be the addition of all these, right? That is this a1 y of n minus 1 plus this x of n plus this b1 x of n minus 1. Okay, so if you observe these two structure, what we have obtained here, right, and what we have drawn here now, right? So here one more delay element has been used, right, while in this first structure only single delay element has been used, right? While two adders and two constant multipliers are there, in both cases two adders and two constant multipliers are there, but this one was the canonic structure. Why? Because single delay element and the order of the difference equation is also 1, while delay element is also used is also 1 number of delay elements. So okay, while here two delay elements are used, therefore this structure is non-canonic structure. Okay, so that is the difference between canonic and non-canonic structures, right? You can also obtain the signal flow graph for this one. Okay, so how its signal flow graph can be indicated? Again, this can be denoted as this adder is there, right? Again, another adder is there, right? Okay, so from this point, again, this, what you can say, that this delay branch is there, right? Z inverse. Here also a delay branch is there, right? Z inverse. Here is your output y of n or y of n or capital Y of z, right? Here the input is x of n or capital X of z, right? Okay, so from this point again, this constant b1 is here, feed forward, right? And this is feedback constant a1 is there, correct? So this is the signal flow graph for this second structure. Okay, but it was non-canonic. Okay, so that is the difference between canonic and non-canonic structure. So let's see the advantages of representing the digital system or discrete time system in block diagram form. Okay, so what are the advantages of it? So we'll just list out some few advantages. So first one is, just by inspection of the block diagram we can identify the computation algorithm. Okay, so first one is, we can easily, from the block diagram we can easily write the computational algorithm. Okay, second one is, the hardware requirement can be easily, hardware requirement can be easily determined. Okay, even variety of equivalent block diagram presentation can be developed, okay, from this transfer function. Variety of equivalent block diagram presentation can be easily developed using the transfer function, right? So when you are obtaining variety of equivalent block diagram representation, you can select the best one. Just for example, in this case, in this canonic structure only single delay element is there, while two adder and two constant multipliers are there. While in this case you can observe that two adders, two constant multiplier, while two delay elements. So one more delay element is required in this non-canonic structure. So instead of using this realization, we can go with this realization for implementation, hardware implementation or software implementation of the given digital system. Okay, because here the number of blocks required or operation required are less compared to this one. Okay, so that is nothing but this third advantage of block diagram representation of the given digital system. And fourth one is the relationship between input and output can be easily determined. Between input and output can be determined. So these are the some of the advantages of representing the digital system or discrete time system in block diagram form. Okay, so in today's session what we have seen how to realize the given system by using these basic building blocks, that is addition, multiplication and delay elements, right? So only these three basic building blocks are required for realization of any IR or FIR system. We also seen that why these constants, that is a1 and b1, or these ak and bk, are called as feedback and feed forward coefficients, right? Delay coefficients. We also seen one example where we realized the given system using basic building blocks, as well as we obtain its signal flow graph. Then we have seen the difference between canonic and non-canonic structure. For the same difference equation, we have canonic structure as well as its non-canonic structure, right? Then we have seen the advantages of representing the digital system or discrete time system in block diagram form. Okay. So in next session, we'll be discussing basic structures for IIR systems, where we'll see direct form realization of infinite impulse response system. Thank you for joining this session.